Problem 951 also deals with neutrons scattering off of protons. So problem 951, it is found experimentally that in the elastic scattering of neutrons by protons, where the two masses are about the same, at relatively low energies, the energy distribution of the recoiling protons in the lab system is constant up to a maximum energy, which is the energy of the incident neutrons. What is the angular distribution of the scattering in the center of mass system? So what we have is these protons in this lab frame are stationary, and these neutrons are whizzing around, colliding into these protons. But in the center of mass frame, these two objects are about the same mass, and so that means that these two things are coming together at about the same speed. So what we want to know is, what is the angular distribution in the center of mass frame? So initially we have this neutron is coming towards this proton, and they're coming together at about the same speed. And final is we have this neutron scattering off that way, and we have this proton recoiling off this way, where this is angle theta, and of course this is going to be pi minus theta, and that's phi. So we have the angular distribution in the center of mass frame. So what is the angular distribution? It is the number of particles scattering off at a certain angle. Certain angle. So dn by d omega. So the angular distribution for the protons in phi should be the same as the neutrons in theta. So what that means is dn of our neutrons by d omega prime in theta, because this is the center of mass frame, is going to be equal to dn of our protons by d omega prime of phi. Okay. So this tells you that the energy distribution is constant where dn of our protons by dt is going to be constant. And so we have is dn p by d omega prime is going to be dnp by dtp times dtp by omega prime. So this we know is going to be some constant. And so what we need to do is calculate dTp by d omega prime. But what we know is T2 by T naught is 2 M1 M2 M1 plus M2 squared 1 minus cosine theta. So it might not be the form that you thought we were going to use. Normally you would think that it's going to be this cosine squared eta, but if T1 over T naught is 1 minus this, and we have T1 over T naught plus T2 over T naught is equal to 1. So we have, since these masses are the same, 2m squared over 2m all squared 1 minus cosine theta. What we get is 1 minus cosine theta divided by 2. But cosine theta is equal to cosine squared theta by 2 minus sine squared theta by 2. And this is 2 cosine squared theta by 2 minus 1. So what you get is 1 plus cosine theta divided by 2 is equal to cosine squared theta by 2. But this is 1 minus sine squared theta by 2. And so what you get is 1 minus cos theta divided by 2 is equal to sine squared theta by 2. There's probably faster ways of doing that, but that's the way I just did it. So 1 minus cosine theta divided by 2. And so this is sine squared theta divided by 2. So now the kinetic energy of this proton, or T2, is going to be T naught sine squared theta divided by 2. But we want to know what this is in terms of phi. So T naught sine squared pi minus phi over 2 is T naught cosine squared phi divided by 2. So then change in the kinetic energy of the proton is going to be a change in T naught cosine squared phi by 2. But T naught is, of course, the initial kinetic energy, so that doesn't change. So we get negative T naught. We get 2 divided by 2 sine phi by 2 cos phi by 2 d phi. And don't forget, we had d omega prime in theta is 2 pi sine theta d theta, and so d omega prime in phi is also 2 pi sine phi, d phi. So then dTp, the change in the kinetic energy of the proton by d omega prime in phi is negative T naught divided by 2 pi sine phi by 2 cos phi by 2 over sine phi. And we get d phi by d phi. So those are just going to be 1. But remember, we've used this before. Sine phi is going to be 2 sine phi by 2 cos phi by 2. So this is going to be negative T naught over 2 pi sine phi by 2 cos phi by 2 divided by 2 sine phi by 2 cos phi by 2. And so that is negative T naught over 4 pi. And that gives us, remember from before, dNp by d omega prime phi is going to be some constant times now negative T naught over 4 pi, and this is dN of our neutrons by d omega prime, in theta. So what this tells us is that there is no angular dependence, right? And if you think back to billiard ball collisions, this is what we got for billiard ball collisions as well.